So I believe the last time we actually already stated that we're about to discover that what spin is. Spin is, in technical terms, is the highest eigenvalue of the generator of rotations for a given representation. And it turns out that there are different kinds of representations. And so let's write that down, just to summarize what we are going to discover. So what is spin? Spin is the highest eigenvalue of Ji, where Ji is the I generator of rotation. They're all the same, right? So by rotational symmetry, it's doesn't matter which one you choose, J1, J2, or J3, but usually we do choose J3. And in particular, what we're going to show is that i.e. J3, what we're going to show is that the two numbers, one is L, one is M, and J squared is given by L times L plus 1. That's the eigenvalue of J squared. But what is L itself? L itself is actually the maximum for L max is in fact, N max, I'm sorry, is actually L. So, and N min is actually minus L, i.e. N runs between minus L and L. And so spin is just the maximum here, L. So when I say spin L, it just means the largest, for a fixed representation, the largest eigenvalue of J3. And what we're about to discover is that L, spin L, can be both half integer and full integer. So full integer is 0, 1, 2, 3, and so on. Can also be half integer, 1 half, 3 halves, 5 halves, and so on. And nothing else. These are the only possibilities. And so we have already seen these guys actually. So the spherical harmonics is the position representation of integer spin. So what we haven't seen are the half integer guys. And that's going to lead us to the concept of fermions. Okay, so we'll talk about that in a little bit. But what's key to understanding this is what we defined the last time, are the raising and lowering operators. J1 plus I plus minus I J2. Yeah. The next time I'm going to announce that I will still teach during sports day. Yeah. Because I cannot remember sports day, and I don't go to sports day anyway. So, okay, so, let's see where that comes from. So remember what we actually did the last time was that we defined an eigenvalue called lambda for J squared. And what we showed was that there is a bound. Using the raising and lowering operators, we showed that there was a bound. bound obeyed by lambda and m squared. So it went like that. And we also showed that every time you apply j plus minus to lambda m, that gave us something proportional. So the proportionality factor we haven't worked out. We will do that probably today. But this will lower or raise, depending on whether you choose minus or plus, it will lower or raise the m value by 1. Okay? And so the argument went like that, right? So if you keep applying j plus for a fixed lambda, right? So lambda and m are independent. In principle, they are independent because they come the eigenvalues of two different operators, two compatible observables, but they're two different observables, right? Compatible but different. One is J3, one is J1 squared plus J2 squared plus J3 squared. And so for a fixed lambda, you can keep applying J plus again and again. So you'll go from m to m plus 1 to m plus 2 and so on until you can get as large eigenvalue for J3 as possible. So m can become as large as you want. But if m becomes as large as you want for a fixed lambda, it will surely at some point become larger than lambda. So that's a contradiction. This will contradict directly what we're finding over here. Same thing, if you keep applying the lowering operator, well, at first m will get smaller and smaller and smaller, then it will pass 0, and then you will get more and more and more negative, and then by the time you're, you're a little tired, you will realize that m has gone so negative that the square has become so large that it would have exceeded lambda, right? So again, it will be a contradiction. If there were no, so let's summarize this. If there were no if j plus or minus to the n going to infinity does not terminate then it will contradict. So m, the resulting m, will be in fact bigger than lambda, m squared, I'm sorry. The resulting m squared will be greater than lambda, which will lead to a contradiction. Okay? So therefore it has to terminate. Right? This is called proof by contradiction. And so it has to terminate. That means there must be a maximum. There must be an m max, where when I apply the raising operator to it, it has to give me the zero it has to give me the null vector. It has to give me the zero vector. That's how it terminates. Right? There's no other way it terminates. Likewise, there must be a minimum such that when I lower it one more time, it terminates, meaning it gives me the zero the zero vector. Okay. And now the question is, what are these minimum maximum? So in fact, we can use these conditions. Okay, so because of the zero vector, we can now take the norm of the zero vector. The norm of the zero vector is 0. So therefore, lambda and max j plus dagger, this is just a dagger of the left-hand side, projected onto itself which means that J plus lambda and max must be 0. Okay? J plus dagger, J plus, we worked this out yesterday. Not yesterday, Monday, right? J plus and J plus dagger, so maybe I'll write it down over here. J plus minus dagger, J plus minus, we showed the other day that this is in fact J squared minus J3 squared, and then minus plus J3. Okay. And therefore, this guy in particular is the plus sign, so it is just simply lambda and max, and then we have J squared minus J3 squared, and then it's a plus sign, so we have a minus J3 lambda and max equals to 0. And this is where the eigenvector equation comes in. J squared applied to either left or right will give you lambda, and then J3 applied to either left or right will give you m squared, m max squared, and then this will be minus m max will be 0. Okay, so in fact, so lambda is in fact m max squared plus m max. And likewise, yeah, that's right. And likewise, we can do the same trick for this guy. So lambda and min J minus dagger, J minus applied to lambda and min must be 0. Okay? And again, because the norm of the 0 vector is 0, and what is that? This is now J squared minus J3 squared plus J3. And then lambda and min. Lambda and min equals to 0. And again, you can use the eigenvalue equation that obeys, and you get lambda minus n min squared plus n min. So if you move it to the right hand side, lambda will be equal to n min minus n min. Okay, so lambda is fixed. Right? So lambda is fixed. So now you can use it to solve for n min in terms of n max or vice versa. Okay? And let me do it for, let me solve n. So let me do this. N max squared plus n max minus n min n min minus 1 equals to 0. Right? And this is just a quadratic equation. And so, n max, what would it be? It will be equals to minus b. Minus b is minus 1 plus or minus square root of b squared minus 4ac, which is plus and min minus 1 divided by 2. Okay? And let's work that out. Well, anyway, it's just algebra. So what I have, what I got was that this is in fact n max, you can check me, is minus 1/2 plus or minus n min minus 1/2. Okay? And so what does that mean? Let's work it out. So if you choose the plus sign, you will have n max minus 1. If you choose the plus sign. If you choose the minus sign, you get n max, n min, oops, I'm sorry, n min yeah. So n max is equals to either n min minus 1, which is completely nonsense because this is maximum. It should not be minus 1 of the minimum. Otherwise, it wouldn't be called a maximum, right? So this is a contradiction. So this is a contradiction. But this is okay. It's okay for the maximum to be negative of the minimum. So if the minimum were minus 10, maximum will be 10. And that's in fact exactly the unique solution. Okay? So that means that what we must have is that n max must be a positive integer because it's opposite sign of each other, right? So if it's the maximum, this guy better be the positive guy, and the n min must be the negative guy. So now we'll redefine this to be L, okay? And so therefore n min will be equal to minus L, given this, right? So I'm just relabeling it, because now we've discovered there is a maximum, and the minimum is just a negative of it. So maximum is L, and we've recovered this statement over here. Okay? And then we plug it back into lambda. So lambda itself is what is now given by n max squared plus n max. And that's exactly L times L plus 1. Right? Because this is n max, this guy here. Okay? And so we have derived this quite fundamental result that applies to essentially all fundamental quantum mechanical systems that are quantum mechanical particles that are rotationally invariant. All elementary particles in nature are like that. Because the Hamiltonian is invariant under rotations, it will be very strange actually if one day we discover the Hamiltonian of some fundamental system is not rotationally invariant. Okay. If you have a macroscopic system, maybe it's okay because you can turn on a magnetic field, you can turn on an electric field, and so on. But at a fundamental level, it will be very strange if sorry, I didn't mean to say this is an integer, but this can be half integer or integer. Okay, but have I shown that? Let me just make sure. Yeah, so this is the only thing I haven't shown yet, okay? So remember, yeah, let me just finish saying, right, that, so this is a very fundamental result because all elementary particles, for example, have spin spin L. Okay, because the Hamiltonian is rotationally invariant. That's why you spend so much time understanding spin, because it's such a fundamental property. So I have now shown that L is either integer or half integer, but let's now show it. So remember that, again, by the raising and lowering operator, you know that the minimum and maximum must be connected to each other by the following. So it must be that when I apply the raising operator n times, there is some n where I can get from n minimum, I'll drop the lambda label, to n maximum. This will give me some number, some coefficient, times n maximum. Yeah? Because you go from n minimum, you can go to n min plus 1, n min plus 2, all the way to n max. Okay, there must be some n that will do this job, because that's what we're shown. It will keep increasing the n until I get to n max. So therefore, n min plus n must be equal to n max. But we have just shown that n max and n min are L and minus L. Right? So this guy is minus L, this guy is L, and therefore n itself is actually equals to 2L, which means in turn that L itself is n over 2. So this is also very important. Okay, so n, I assume, is integer. And so, therefore, L itself, the maximum eigenvalue of J3, or really J1 or J2, doesn't matter, the maximum value of the rotation generator, we have discovered, is an integer divided by 2. So this integer, if it's odd, will give us half integer spin, like I said over there, 1 half, 3 halves, 5 halves, and so on. And when n is even, then you get integer spin. Right? These are the possible solutions. And we don't have any other constraints. Right? We worked it all out and we discovered that, okay, this is what the math seems to tell us, that we should have these two different solutions. Okay? So like I said, the spherical harmonics that we did the other day, in fact, is nothing but the position representation on the sphere of the eigenvector Lm, where L is integer. Okay. In fact, we'll show later on that you can ask this question. So this discussion is in Sakurai. He asked this interesting question: is there a spherical harmonic for spin half? In particular, he did it for spin half. And the interesting, so it's an interesting question that you can actually answer, and the answer is no. It's not possible to get y 1/2 plus or minus 1/2. It's just not possible. Okay. And we might talk about it in a little bit. But so, given that we've done this, let me in fact move back to spherical harmonics and say a little bit more about it based off of what we have talked about. Okay, so that we can reinforce this more algebraic approach. So whenever it's available, this algebraic approach is actually can be very powerful because it's very general and doesn't require that you know the explicit wave functions. Okay. Any questions for me?
So,
Yeah. Yeah.
do you mean that the elementary particles only spin up and spin down? That's true state?
No, I mean spin L, right? I just mean that they can take, in principle, they can take all spins. There are other constraints that come from quantum field theory, but for now, I'm just going to leave it here, which is that they can be spin 0, right? The Higgs boson is spin L, right? So L can be, so what we know in particular is the Higgs particle is spin 0, okay? The electron and its antiparticle, the muons, the taus, the neutrinos. The neutrinos are different species, but electron neutrino, muon neutrino, tau neutrino is paired with these electron, muon, and tau. Maybe I should write it this way. These guys are, and then these guys are spin half. Also the quarks, right? The quarks are up, down, top, bottom, and strange and charm, right? So also have spin half, right? And then we have spin 1, given by the gauge bosons, right? The photon, the gluon, the blues, the Z's, and then we have spin 2, gravity. Okay, so even if you didn't know about elementary particles, you can predict that the fundamental constituents of nature, right, should have these quantum numbers. That's what I'm saying. Right? Anytime your Hamiltonian commutes with the generator rotations, what does that mean? It means that it's compatible, right? The Hamiltonian is compatible with J squared and J3. And then you will have this conclusion, right? You will be able to label your states using spin. That's exactly what an elementary particle is. The quantum state of the elementary particle are simultaneous eigenstates with J squared and J3. At least in the rest frame. It's a little bit more sophisticated. You know, you're doing QFT, but essentially it comes down to this. Yeah.
So,
yeah.
I think that lambda equal to L times L plus 1.
Yeah.
This constraint is not the first time show up, right? I think we can get these ones when we solve spherical harmonics.
So what I'm doing here is more general, right? I've not made any assumptions, but for spherical harmonics, good. So yeah. So here's the thing. So we showed that the Laplacian on the sphere applied to spherical harmonics in 3 dimensions was L with a minus sign. L times L plus 1 YLM. And furthermore, we were able to show that, you have to do some calculus, but you are able to show that the orbital angular momentum, okay, so let me just write it down. If you write down theta phi, we use a homogeneous polynomial of degree L, and we use it as a trick, right? We demanded that the solution was homogeneous as well, and then we got here, right? You remember? So this is a specific ansatz that we used to get from here to here, a specific prescription, right? So you can ask, you can fairly ask the question, how do you know there aren't other solutions? So Weinberg has a more sophisticated analysis, right? But I think it's more general to just go straight to the algebraic discussion and show that just from the raising and lowering operators constructed from the Lie algebra, you can show very generally that there cannot be more solutions, right? And that's what we did here, right? So if you go through the proof that we went through, you will see that it tells you there cannot be other solutions. Yeah. So this is subsumed. The spherical harmonic, as far as the eigen vectors, the eigenvalues are concerned, they are subsumed within the algebraic discussion, but not the eigenvectors, right? So indeed, the construction of the spherical harmonics themselves, that does require explicit, for example, you need to know explicitly what this guy is, and then we solve that this guy was proportional to e to the I m phi, right? If you remember this, in fact, we'll do it again. That part requires explicit knowledge of the differential operators, which then allow us to solve for y of n explicitly, right? But the eigenvalues themselves, the algebraic method is more general. Okay, so in fact, let's do that. So let's come back to our discussion of spherical harmonics. Okay, and what I want to do is to, in fact, remind you that all of this discussion, as I've just mentioned, comes from the Lie algebra. Everything follows from this commutation relations. But you can also work out what these guys mean in the position representation. Right, so you can ask the question, J1, what is it in the position representation? And you will discover J1 is I times sine theta, sine phi, d theta plus cos phi. These are all in my notes. In fact, I think it's your homework problem. Cotangent theta d phi acting on r theta phi psi. R theta phi J2 psi is instead I, and then minus cos phi d theta plus sine phi cotangent theta d phi acting on the state, and then r theta phi acting on sandwich between J3, or rather J3 sandwich between these guys, is equals to minus I phi, acting on the state. So this is something that you can work out explicitly using the fact that you know that Ji is in fact epsilon ijk xj pk. Okay, so previously, remember that, why is that so? Because ji itself is in fact 1/2 epsilon ijk jjk. And then jjk, previously we have already shown that this is xjpk minus xkpj. Okay, so if you forget, if you just look at your notes, we derived this from the position representation. And this is orbital, so this is for orbital angular momentum, which just means the rotation operators are acting on these position eigencats. Okay, but using the now using the spherical coordinates. So, what you would discover is that Ji is just a cross product between position and momentum, right? This is not how you learn it in classical mechanics, but now you've seen, now that you know quantum mechanics, you're seeing a more fundamental, I would regard this as a more fundamental derivation of x plus p. Now, for spherical harmonics, what is important is that YLM, as I mentioned, is the theta phi LM matrix element, right? And so what it means is the following. Remember that theta phi J3 LM is in fact given by this minus I d phi, but at the same time, J3 applied to the eigenstate has to give you M, right? And so this we solved already. So I won't. In fact, let me just write it down. YLM, and this is YLM. And so in fact, that's why we know that YLM itself is proportional to e to the I m phi, with the boundary condition that YLM of phi plus 2 pi is equals to itself. It's a continuous function. Right? Otherwise, it would mean it would jump by, which you don't want that to happen. At least not for the spherical harmonics. If you want it to be a complete set on the sphere. So, but you can also ask, what about the theta dependence, right? So this is also where the raising and lowering operator comes in. So remember that we've already figured out, theta phi. We have already figured out, we just used it in fact, that J plus, in fact, applied to LL, right? Remember, L is the maximum eigenvector value of J3, and L is now maximum. So that means if I apply J plus to this guy, I better get 0. So from these guys, you can work out what is J, these two first guys, you can work out what is J plus. Okay. In fact, it doesn't have to be LM. You can work out what is J plus minus. Right? I'll just write it down explicit directly here. You will discover that J plus or minus looks like the following. Yeah, okay, good. So it looks like the following. So this will in fact give you the following equation. It will give you e to the I5. In fact, you can expect e to the I5 because it has to increase the n value by 1. And all the spherical harmonics are proportional to e to the IM5. So to add one more, you've got to multiply by e to the I5. Right? And then you have a differential operator. D theta plus I cotangent theta d phi. Okay, so J plus is actually this guy acting on theta phi LL, but that's just at YLL theta phi equals to 0. But you know that the phi part is just e to the I phi, e to the IL phi, right? So this guy will just bring down e to the I phi, and then you will have L plus 1 from this guy. And then if you just define YLM to be e to the IM phi, and let me just call it Y hat L of theta. Okay, then what will happen is that now I will have d theta plus, Y hat, YLM, I still need an M. Then I get I5 acting on e to the IM5 will bring down, will give me a minus M, and actually it's L, so it's minus L cotangent theta acting on Y hat LL of theta. Okay? And likewise, so what you have is that you now have an ODE, you see it's an ODE for YLL hat. Yeah? Because this drops out anyway. So there's now just an ordinary differential equation, and it's a first order, let me just write that down, first order ODE, which means you can fix the form of Y hat LL up to the overall coefficient. And the overall coefficient, of course, this is supposed, if this is some wave function of a sphere, you will just make sure that the norm is 1. Right? So we'll fix that later, but that means you can basically fix what this guy is, up to an overall number. Okay? So likewise, and let me just finish it over there. And so in fact, let me tell you what the answer is. Y hat LL, you will discover in your homework, you can write it in terms of cosine theta. It's in fact, let me just write it down. It's in fact proportional to sine theta to the Lth power. Okay? And like I said, the normalization is something that you'll have to work out by normalizing it to 1. And then you can do the same thing to the lowest eigenstate, right? So you will find, you can do, so similar, you can find similar argument for the lowest eigenvalue for M. And you'll find that YL minus L hat, or let me just write down for YLM, is proportional to e to the minus IL phi, and then the sign dependence, the theta dependence, is the same. Okay. So how do you get the other M's? But that's where the raising and lowering operator comes in again, right? So, in fact, let me write that down and then I'll let you guys go. Okay. I'll probably talk about it again, this last part, because it's a little bit technical. So we know that the lowering operator on LL will give me, in fact, so let me put it this way, it will give me, if this guy acted on LM, if I acted L minus N times, then this will in fact give me something proportional to YLM, right? Because I'm sorry, L, right? So if I acted on the highest eigenstate, then L minus L plus M will give me M, okay? And what you discover is that if you use that, you will discover that starting from this higher state, right? So we know that this is in fact YLL, right? So in fact, YLL itself is therefore some number times sine theta to the L times e to the I L phi. Then that means that this guy is in fact the lowering operator acting on this guy L minus 1 times. And what you can show is that it's a little bit of algebra, so I think I'll do it again next time. You will show that this is in fact proportional to e to the I and phi. This you know because it's going to give you YLM divided by sine theta to the nth power. So this is the part that's not so obvious. And then you differentiate with respect to cosine theta, L minus n times. Basically, this part is the lowering operator, but it's not obvious, right? You have to do some calculus to show this. But now acting on sine theta L. Okay. So I wrote down 1 minus cosine squared theta to the L. I need to check whether this is the right power, but basically you'll find that by working with the lowering operator, you can show that this is true. And what people do is they usually define for n greater than 0, they define YLM of theta phi to be in fact this quantity here. Let me just write down the whole thing. Minus 1 to the L over 2 to the L factorial, and then square root of 2L plus 1 over 4 pi times L plus n factorial over L minus n factorial, and then e to the I n phi over sine theta m, and then it is d cosine theta acting on L minus n times on 1 minus cosine squared theta to the L. Yeah, so this is actually sine squared to the L. So when sine theta is L, when n is L, then you get sine L, which is correct. Yeah, so this power is correct. So this is actually spherical harmonics for n greater or equal to 0. And this numerical factor here is not obvious, but comes from normalizing the spherical harmonics to 1. Right? So if you square this and integrate over the sphere, you will find that this is in fact 1. This gives you this numerical factor up to a normalization. And then you can ask, what about the n less than 0? N less than 0 is gotten by this relationship. YL minus M is equals to minus 1 to the M times YLM complex conjugate. Okay? And that gives you all the M's. M from minus L to L. Any questions? That's a definition. It's a definition because it chooses the phase convention. Actually, even this is a phase convention because this only fixes the number up to an overall phase, right? So this is also a choice of phase. But once you choose this phase and you define the minus negative M through this, then you have fixed all the phases, right? But this is a consistent definition because you can show that it will obey the minus M YLMs, the negative M's, will obey the right eigenvalue equation. And that's all you need. Yeah. Any questions for me? No? Okay. See you guys next week.